Hello, this is Mahanda Didia. This is an on-demand dynamic supplemental book on liquid formulation that makes learning faster, better, and easier. This is continuation of Module 1, Introduction, and this is the second video in this module. In this submodule, reader will see embedded videos as an example that would help the reader visualize the concept without relying on mathematical equation. The second video in the first module on Introduction to Liquid Dosage Form is physical-chemical properties. Specifically, we'll spend time on surface tension and rheology. First property is unique to liquid is a shape of liquid. Liquid are incompressible, i.e. if you apply force, they do not lose their volume substantially. Though the volume is fixed, the shape is not. Shape of liquid conforms to its container. They are pourable, flowable, and spreadable. We will look at the video to understand this particular concept of shape and volume. So what happens to volume of water when it's transferred between different containers? Here we have a water with a dye, so it's easier to see, and it's poured from a beaker into a plastic container. Entire volume is dispersed, and you can see it's taking the shape of that container. We take that same volume of water and transform into a different shape container, and again liquid will take the shape of that container. We can continue that process a couple of more times to see it. Different types of containers are shown here. Again, liquid is poured and the shape of the liquid is changed. And this is the final container, a large beaker. In that, again, liquid shape changes. If we put that liquid back into the original container, you will see that the volume of the liquid remains the same. So this particular concept is extremely important for liquid products. Next concept we want to look at, it is surface tension. Surface tension is an attractive force that pulls the surface molecule on the surface into the rest of the liquid. So these molecules on the surface are pulled inside. That creates the surface tension. And mathematically, this is given as force equals to 2 times the surface tension multiplied by length. The unit of surface tensions are dynes per cm, or more preferably Newton per meter. Newton being the unit of force. We want to now look at it to see what is surface tension and how does it behave at a molecular level and under simulation, so that it's easier to understand what is surface tension. We will look at this as a water molecule. And water molecules are attracted to each other by hydrogen bond. Water molecules on the surface have less hydrogen bonding, i.e. there is nothing on the top, and they are much stronger. The stronger hydrogen bond then attract downwards to the water. We'll simulate this in this molecular dimension, and you will see that water, oxygen is always attracted towards hydrogen, and that's due to the hydrogen bonding. And hydrogen bond is formed between hydrogen and the oxygen. Hydrogen bonds are shown here. You can see that oxygen and hydrogen are attracted towards each other. These bonds are sufficiently strong to hold the structure. We can move the molecule in motion and you'll see hydrogen bond formation and hydrogen bond creation and breaking. You'll notice if we add more water molecules and they will form hydrogen bond. What you will see if we rotate the molecules, the surface of the molecule has less hydrogen bonding, i.e. they are strong, and that's the reason for surface tension and the shape of the water molecule. Spherical in nature. So surface tension can be reduced by different agents such as surfactants, electrolytes, temperature. Surface tension of some of the liquid is shown here. Example is water. Water has a surface tension of 0.07 Newton per meter compared to ethanol has a higher surface tension of 22. That means it would require more force to pull ethanol molecule into the system. This is important to understand. Next two properties are unique to liquids. These are viscosity and rheology. Viscosity is resistance to a flow under shear stress, i.e. under the force. It's given by equation force over unit area, that's a shear stress, is equal to viscosity multiplied by velocity gradient or shear rate. So if we apply a force on a liquid, liquid will flow depending on its viscosity. Rheology is flow and deformation, and liquids are classified into Newtonian and non-Newtonian. So we want to know what is viscosity and what is this resistance to a flow. So we will look at two different containers, one containing water and other containing glycerin. And a lead ball will be dropped in each of the containers, exactly identical, and the ball is going downward due to the gravitational force. So viscosity can be observed through this of lead ball into two systems. And as you can see, the lead ball moves much faster into water compared to glycerin, indicating, so you can see glycerin is more viscous than water. It requires more force to move glycerin. Essentially identical lead ball, the water ball drops faster compared to glycerin. Rheology is deformation of liquid under shear stress. So when we apply the force, liquid will flow. And it's going to be classified as Newtonian and non-Newtonian. So what is Newtonian fluid looks like? And what does a non-Newtonian fluid looks like? In this video, we will observe that. First is a Newtonian fluid and second would be non-Newtonian fluid. So here's an example of Newtonian fluid. Deformation is constant. Non-Newtonian fluids, when we apply shear stress, the flow property changes. Shear stress has to be applied in order to make product flow. Newtonian and non-Newtonian fluids. And one can visualize this very, very clearly in this video. We will now look at the graphs of Newtonian and non-Newtonian fluid. Shear stress F divided by A, force over unit area, is proportional to the velocity gradient or shear rate. Shear rate or velocity gradient is measured 1 over time unit. For Newtonian fluids, if we apply shear stress, as we increase shear stress, shear rate proportionately increases. Non-Newtonian fluid, as we apply more shear stress, they are not linear. They increase rapidly and then eventually do not change. These are non-Newtonian plastic. Very critical is yield stress in many of the cosmetic as well as pharmaceutical products. So shear stress is applied, product will not flow until it reaches yield stress and then it starts flowing. Non-Newtonian pseudoplastic shear thinnings are very common in cosmetic and pharmaceutical formulations. Their flow properties, i.e. forces applied, they start thinning and eventually reach a plateau point. In a viscosity versus shear rate, Newtonian fluids, viscosity remains constant. It does not change. Pseudoplastic, as we apply more force, the rate of spreading or rate of flow increases. Similarly, plastic, and there are dielectric fluid in which viscosity increases as we apply shear rates. Cosmetic as well as pharmaceutical topical products are used by spreading it, and spreading process involves yield stress, viscosity. This can be seen in this video. So in order to measure these properties, mechanical devices such as shown here, texture analyzers, are used, and they provide better understanding of structure, friction, and spreadability rather than using sensory analysis in human. So when we take a cream, we need yield stress, a certain force. Force is applied, viscosity takes over. It starts spreading, product like gels, toothpaste. So viscosity is shear rate dependent. And the last step is friction. We will have a friction that's going to provide the feel for the product. All three properties are involved in sensory analysis of creams and lotions. So let's look at liquid classification, its description, and physical properties. Solutions are monophasic, they're clear and homogeneous. They generally have a Newtonian flow. When we apply shear stress or force, its shear rate will proportionately increase. Creams are biphasic. Emulsions generally have a plastic flow, and many creams will have a moderate stress yield, or they may be thixiotropic. It requires a force before it starts spreading. Lotions are biphasic. They're emulsions. They have a pseudoplastic flow. They are pourable, and there's a very minimal yield stress required to make it flow. Gels contain stiffening agent. They provide stiffness. They are generally a plastic flow, requires moderate shear stress force to spread. Ointment, similarly to gel, are plasticky in nature and requires stress. Paste clearly are plastic flow and have stress yield. Syrup are monophasic, they're clear, homogeneous. They are Newtonian flow, but they are slightly viscous. Nail polish removers are monophasic, very Newtonian flow. If you apply pressure, it will flow. They're slightly viscous and they are generally used with an applicator. Nail polish gel, on the other hand, is a biphasic with gel base and colors, heavy pseudoplastic flow, and highly viscous. So now we can relate nomenclature, classification, description to physical property, specifically rheological and viscosity of the product.